If the technological history of a spacefaring species were compressed into a single day, humanity has only just opened its eyes. And yet, within that microscopic interval, we are already contemplating space probes that could approach relativistic speeds. These proposals do not depend on exotic physics or hypothetical breakthroughs that may never occur. Instead, they rely on ideas that are quite straightforward. A very small spacecraft, pushed by powerful laser arrays until it reaches a meaningful fraction of the speed of light. The interesting reality of these probes is that they act as kinetic batteries. They carry the cumulative energy transferred to them by the lasers stationed on Earth until the moment they collide with another object. In the Breakthrough Starshot model, we spend roughly 60 terajoules of laser energy in a single 10-minute burst to give the probe roughly 1.8 terajoules of kinetic energy. At that point, this tiny 1-gram probe, no heavier than a paperclip, possesses the destructive power close to 500 tons of TNT, making it comparable to a small tactical nuclear warhead. Such systems are currently proposed for scientific purposes only, instruments designed to explore nearby stars and transmit information back to Earth. But there is an uncomfortable detail. Physics does not recognize the difference between a probe and a weapon. An object traveling at a significant fraction of the speed of light carries enormous kinetic energy. At those velocities, even something with the mass of a small spacecraft can release catastrophic devastation on impact. Not because it was designed for destruction, but because motion itself contains energy. In other words, a relativistic probe and a relativistic projectile are physically indistinguishable. The difference exists in human intention, but not in the equations that describe momentum and energy. This realization leads to a key conclusion. The capability to launch relativistic projectiles does not belong exclusively to ancient or galaxy-spanning civilizations. It is an inevitable byproduct of early interstellar space exploration. And once this reality is understood, the strategic structure of the universe changes in a profound way. If small objects traveling at relativistic speeds are inexpensive to launch, then offense acquires a structural advantage over defense. Destroying a planet requires only that one attack succeeds, while protecting it requires that every possible attack fails. Defense must succeed everywhere and every time, while offense needs to succeed only once. Launching a relativistic projectile may require significant energy, but the cost is borne only once. The defender, by contrast, must construct and maintain a vast system capable of detecting and stopping such threats from every direction and remaining active indefinitely, just to prevent an attack that may occur only once in 1,000 years. Under these conditions, if relativistic strike capability is by nature accessible to all early space civilizations, then almost every civilization in the universe acquires, at least in principle, the ability to end another civilization's history. The galaxy stops being a place where annihilation is the privilege of vast empires. Instead, it becomes a place where catastrophic power lies within reach of any society capable of interstellar travel. The universe is therefore not full of demigods. It is full of mortals wielding godlike power. What makes this conclusion especially disturbing is how ordinary the underlying technology appears. The path toward such capabilities is paved with engineering projects that scientists have already begun to explore. One of the earliest serious attempts to treat interstellar travel as an engineering problem rather than speculative fiction emerged during the Cold War. In the early 1970s, scientists undertook an ambitious theoretical study known as Project Daedalus. Their objective was not to build a spacecraft immediately, but to determine whether a probe could reach another star using physics that was already understood and technology that was plausibly within reach of a late 20th century civilization. And the conclusion was resounding: yes. The proposed spacecraft was immense. The Daedalus probe was designed as a two-stage fusion-powered vehicle. Its propulsion system relied on inertial confinement fusion, using small pellets of deuterium and helium-3 ignited in rapid succession behind the spacecraft. Each tiny fusion explosion would produce a burst of plasma that would be directed by magnetic fields to generate thrust. Over the course of several years, millions of such micro-explosions would gradually accelerate the probe to roughly 12% of the speed of light. 50 years after launch, it would pass through the Barnard star system, gathering scientific data during a brief but invaluable flyby. The energy requirements were enormous and the engineering challenges formidable, yet nothing in the concept required physics beyond what was already known. The interstellar travel seemed very difficult, but not forbidden. At the same time, Project Daedalus quietly revealed something rarely emphasized outside technical discussions. If such a spacecraft were to strike an exoplanet at its peak velocity, it would release an amount of energy far exceeding the combined power of humanity's global nuclear arsenal. This was never the intention of the Daedalus designers, and the project was conceived entirely as an instrument of exploration. Yet the implications follow directly from the same equations that govern propulsion. A spacecraft capable of delivering scientific instruments to another star at relativistic speed is, by definition, also capable of delivering kinetic energy on a catastrophic scale. These studies reveal that as soon as a civilization begins to think about reaching other stars, it begins to flirt with relativistic power, not because it seeks dominance, but because the stars are far away, and physics offers only one way to reach them fast enough. All of these projects emerged independently across decades and technological contexts, and yet all of them converge on the same uncomfortable conclusion: the capacity to destroy at interstellar distances is not a rare aberration, but an almost inevitable byproduct of interstellar ambition. If a young civilization can move from its first satellite to relativistic capability in little more than a century, it becomes irrational to assume that such capabilities are rare. And if they are not rare, then the silence of the cosmos is no longer surprising. It is necessary. This was just a short segment from The Geometry of a Hostile Universe, a 160-page framework demonstrating why the Great Silence is not a mystery, but a physical inevitability. It skips the usual sociological tropes and instead starts with an intuitive exploration of relativistic motion and how it leads to a fundamentally hostile universe. To learn more, click the first link in the video description below.